slope field, 6-1. You know, we only have about 6 more sections left before we are officially done with all of the new information you're going to learn in this course. So we're coming down the home stretch. We are on 6-1, slope fields. What we're going to learn about is differential equations and slope fields, which are a huge part of what they're studying right now in calculus and what a lot of stuff is based off of. I do have a 5-point quiz for you this session, and what the first 3 are asking you is basically, is the derivative actually the derivative for these functions over here? So you just want to justify if these functions over here actually do have the derivative at the beginning. So you're just going through and finding those derivatives and telling me yes, that is, or no, that is not. And then in 4 and 5, you are just finding C. So if x and y are given, can you then find C? Okay, which yes, you can, and you are to do so to get your points for this quiz. Okay, so a little review. We're going to look at y equals x squared plus 3. We know that the derivative is 2x. If I gave you x squared minus 5, it also has a derivative of 2x. It doesn't really matter the 3 or the negative 5. They don't really affect anything because they are the constant. Derivatives of constants are 0. But if we reverse the operation, I gave you the derivative, and I asked you to find the integral, or asked you to find the original function, we would have to attach a plus c onto the end because we don't really know what c is. So we just put it there to remind us that there could have very well have been a constant attached. If we do know a little bit more information, we can then find c. So for example, if I told you your derivative is 2x and your y is 4 and your x is 1, then you can now find the exact equation for y. I know my derivative, or my antiderivative would be y equals x squared plus c. 4 equals 1 squared plus c. I'm getting those values from above, and I can solve that for c and get 3. So I know that my actual equation is y equals x squared plus 3. This is called an initial value problem. We need the initial values to find the constant. Any type of equation containing a derivative is called a differential equation. It becomes initial value problems when you are given the initial condition and asked to find the original equation. So this right here would be your example of the differential equation. As soon as I tell you, here's some more information, and you can now find c, that is when you know, okay, now it's an initial value problem. Integrals such as the integral from 1 to 4 of x squared dx, they are called definite integrals because the answer is a real number, a definite number. If I find the antiderivative to be 1/3 x to the third plus c, and I put my 4 in and my 1 in, I'd get 1/3 times 4 to the third plus c minus 1/3 times 1 to the third plus c. And I work that out, I'll get 64/3 plus c minus 1/3 minus c when that negative is distributed in. And our c's always cancel, so we don't even deal with the c's. And so normally when we're evaluating definite integrals, we don't really even care about putting this plus c here because of that minus symbol right there, they will always cancel out. So we get our answer then to be 21. And so the reason why this right here is called a definite integral is because my answer is a number. However, if I gave you an integral like just the integral of x squared dx, he is called an indefinite integral because we cannot actually find the definite value for the answer. Because I don't have an upper and lower limit, I don't have anything to put into my antiderivative. So we would just say my answer is 1/3 x to the third plus c. When finding indefinite integrals, you always have to include the plus c. This is then referred to as a family of functions that satisfies this indefinite integral above. So just understand that the difference here is that he is an indefinite integral. His answer is going to be a family of functions because you have to attach the plus c. But if we go back, his answer right here is going to be a real number because now I have enough information to put my upper and lower limits in and get an answer. That's why he is called a definite integral. Okay, I'm going to go through just some different types of problems that you could see that all involve differential equations or antiderivatives. So right now this question is just saying to solve a differential equation, find all functions y that satisfy the differential equation dy dx is equal to 3x squared plus the cosine of x. When it's asking you to find all the functions y, you are just saying, okay, he is my derivative. What function would have a derivative of him? So if I go through that, I realize, okay, well this is just the power rule going backwards, so I would say, okay, well that would just be x to the third, and then cosine of x is the derivative of sine, so the solution is any antiderivative of that is of the form x to the third plus the sine of x plus c, because it's saying to find all functions y, and that plus c now says here is my family of functions that satisfies that differential equation. Now I'm giving you an initial value problem. Find the particular solution to dy dx is equal to e to the 2x minus 3x, whose graph passes through the point 1, 1.5. If it just said to find the solution to dy dx equals e to the 2x minus 3x, all we would be asked to do is find my antiderivative and put a plus c on the end. But now it's saying, okay, here is the point 1, 1/2 that it goes through, so this is now an initial value problem. I have here two methods to help us solve this problem. Method 1, I know that my antiderivative would be 1/2 e to the 2x. The reason I have to put the 1/2 in front is because of this 2x that I would have to chain on the derivative of. So basically this 1/2 just counteracts the derivative because my derivative here, 1/2 e to the 2x, would be 1/2 e to the 2x times 2. And my 2 and my 1/2 would cancel then to become e to the 2x. Minus then 3/2 x squared. That derivative is 3x. I take my x and raise the power, so squared. 3 divided by then my new power plus c. Don't forget your plus c. I know then that it goes through the point 1, 1/2. So when I put 1/2 in for all my y's and 1 in for all my x's, I get 1/2 is equal to 1/2 e squared minus 3/2 plus c. If I solve that for c and I add my 3/2 over, I'll get 2. If I subtract my 1/2 e squared over, I will just leave it as such, and that is all equal to c. So final problem is not going to have any c's in it. It's just going to be y is equal to 1/2 e to the 2x minus 3/2 x squared plus then my c, which I found over here. So that's method 1. Method 2, we can use the fundamental theorem of calculus to go through and solve this. I know that f of 1 is 1/2. So y would equal 1/2 plus the integral from 1 to x of my derivative. That should look familiar to you. That's the fundamental theorem of calculus. If they tell you all of the information above, I can set it up like this. What I can do then is find my antiderivative, 1/2 e to the 2t minus 3/2 t squared. That's the same as over here. And I'm going to put my 1 and my x in. So I have 1/2 plus what I get when I put x in minus what I get when I put 1 in. If I distribute that negative in, we end up combining our like terms. 1/2 plus 3/2 is 2. My negative 1/2 e squared comes here, and then here is my antiderivative with x in it. So either method should work to solve that problem. We're now going to use an example that you have to use the fundamental theorem because we don't have right now an easy method to find the antiderivative of the cosine of x squared. So this question is asking find the solution to the differential equation f prime of x is equal to cosine of x squared, where f of 3 is equal to 5. So my 5 goes there, plus my integral from 3 to x cosine of t squared dt. I am now done because that is actually a function who has a differential equation of this. I now can use that function to find any f of x value by simply putting it into my calculator. So if I wanted to find f of 5, I can just put in my calculator 5 plus fnint cosine of x squared comma x comma 3 comma 5, and I would be able to find that answer. So this process is completely fine to solve differential equations as well. Ooh, little do-si-do for us there. For now, your antiderivatives are easy enough to find by using derivative rules in reverse and making a few accommodations with constants. For example, the 1/2 in front of that function earlier that had the e in it. So they're pretty simple to find your antiderivatives right now. We're going to get into some processes to help us find some that are a little more complex in later sections. Here's a technique to graph the integral of a function using your calculator. I can graph, for example, this integral, y equals the integral from 0 to x of t sine of t dt. And if I have the 83s, I can put in fnint into y1. I can put in fnint, your function x sine of x, with respect to x from 0 to x. Now, the problem is it can be very, very slow because your calculator has to take a long time to calculate every one of these values. You can change the resolution in your window screen to 2 instead of 1, and it'll speed things up a little bit. You can even go higher. It does burn up your batteries, and it does take a while sometimes. I am going to go to y equals, and in y equals I just put fnint, my function x sine of x, comma x, comma 0 to x. All right. Now, if I change my window around, I'm going to make that -5 to 5. I'm going to maybe make my, I see that I don't need that much in my y's, so let's go maybe -2 to 2. And I've changed, I'm going to just show you how slow it is if I put a 1 in there for my resolution. If I graph it, you can see it creeping in there. Okay? I can stop it by hitting my on button and go back into y equals, or my window. And if I scroll down and I make my resolution a 2 and graph it, it still takes a little while, but it speeds up a little bit. Now, your values aren't going to be as exact because your resolution is bigger, but it does still work. And even if I would go back into my window and make my resolution a 3, you can see it makes even more ground in a shorter amount of time. Okay, we aren't going to take the time to watch this thing. But anyway, rather, this graph is the graph of your antiderivative because you've put in the integral of the derivative. All right, so maybe we will take the whole time to watch it. Slope fields. This is the last thing we're going to talk about in this section. Slope fields are basically just used as a tool, and they're usually done on computers and graphing calculators, but a recent AP test has asked students to draw a simple one by hand. It's really not too difficult. All it means is they give you the derivative. y prime is equal to 2x. And we're just going to pick certain points along this coordinate plane. So my first one is 0, 0. If I put 0, 0 into my derivative, I don't have a y value to put it in, so I'm only going to put 0 in for x. 2 times 0 is 0. So what that means is that at the point 0, 0, my slope, derivative, is 0. And you can see over here that we're just going to draw a very short little hash with a slope of 0 at that place 0, 0. If I move on, if I choose the point 0, 1, if I put that into my derivative, again, I don't have a y to put in, so again, 2 times 0 is 0. So at the point 0, 1, you're going to see a hash with a slope of 0. And we're just going to continue this for different points along the curve. 0, 2, if I put 0 into my x, I'm still going to get 0. So you will see off to the side, my slope there is 0. And what you're going to find is that along this y-axis, all of these points are going to have a slope of 0 because my y value is not a part of my derivative. So 0, 3 is going to have a slope of 0. 1, 0. Now let's see what that does. The point 1, 0, if I put 1 into my derivative, I will get 2. So at the point 1, 0, you're going to see a line with a slope of 2. Okay? Moving along. 1, 1, slope of 2 again. Because again, my y's in this case do not affect my derivative. 2, 0. Now I have a slope of 4. So at the point 2, 0, you're just going to see a more slopey hash. And we go along and you see all of those points would also have the same slope. If I put in negative 1, 0, I'll have a slope of negative 2. So there you see hash going the other way. Negative 2, 0 has a slope of negative 4. Okay, so what we have just done is kind of created the shape of the graph. So if I knew what point it was going through, I could kind of see the shape of the graph at those different points. So if I know an initial condition such as 1, negative 2, right here's that point, 1, negative 2, it has to follow the shape of these lines, and you can see that it is a parabola that kind of follows those lines. What the initial value condition does is it just pins down vertically where this graph is on the coordinate plane. So if it said that it was going through 0, 5, we would just move this guy up and it would be a parabola going through 0, 5 up here. Okay? Alright, I think that's about it, everybody. So, hopefully you've watched. Come in tomorrow with your 5-point quiz, and have a good evening. We'll talk to you later.